So welcome to this pre-recording of a third lecture in a graduate course on supercomputing. So this is lecture 3 on the end of the first week. So we are still introducing the topic. So in this topic of today, the topic of high-level parallel programming, can still be considered as transitional, so this still belongs to the undergraduate portion of the course. It's also a way to indicate that parallelism and supercomputing doesn't need to be so technical. So sometimes what is problematic with supercomputing is that people think that it is a highly technical, highly specialized programming topic. Well, it is not. So that's kind of one of the purposes of this lecture. So I will address high-level parallelism. So what is it? So I actually looked for a formal definition also in the Encyclopedia of Parallel Computing, and didn't really find a very precise definition. So in a way, I will try to describe it or kind of indicate what I feel are the three most important characteristics. So the first characteristic is that it should be familiar. So familiar to people who know how to use computers, who know how to do computations on a computer. So no new language should be needed. So it's not particularly attached to a language. I will address Julia, and sometimes I tell people Julia has a syntax that is very familiar, very similar to MATLAB. If you have never used MATLAB, then that doesn't mean anything to you. So the familiarity is here already kind of ill-defined concept. It should be interactive. So if you use a supercomputer, then often this works via submitting a job for batch processing, because people want to utilize the time on the supercomputer as best as possible. And in some sense, this is already also a drawback. What we mean by interactive computing is also that it is immediate. So the computations start immediately whenever you want it, and you get a quick feedback. The other topic is personal. So we actually live in the time of personal supercomputing. So I'm running this pre-recording on a fast laptop with 8 cores with a very high-end graphics card in it. In some sense, you don't need a supercomputer, but also supercomputing is nowadays also relative. There are very, very important, very performant computers available. So these characteristics are kind of open to interpretation, but it's mainly important because you want to decide first, before you want to go to a real supercomputer, to decide if your application or if your computation is actually suitable for parallel computing. So a prototyped computation will actually help you deciding that. And for the sake of this course, most important, and I would say almost all important concepts we can already experiment with at a high level. Okay, so there is the high-level parallel programming conference series. This has already been going on for a span of 20 years. So I visited the last edition of the high-level parallel programming conference series. I did not copy the entire list of topics, but you see the performance models, the software synthesis, which means that this is part of also the holy grail of automatic parallel code generation. So there are the applications and tools, and then there is the formal model of verification. Most parallel computers execute it out of order, in a different order as it would be sequentially. Can you then still ensure the correctness of your computation? So I want to indicate that high level is certainly not the opposite of low level. It can also be meant to be abstract and formal, so it certainly covers this. It's also not the opposite of technical. So I'm trying to still come to a formal definition. And I think I don't manage to do that, but it can be very technical if one goes to the development of high-level tools that need to analyze the parallel software and try to make it automatic. Okay, so what does it mean for us in this course? So I talked about familiar programming environments. Well, Python has, at least at UIC, in our department, been introduced as the first language to introduce programming. So it's good to introduce programming. That doesn't mean that it is easy. So most of our undergraduates may not rate Python as easy. Nevertheless, it was also introduced based on the availability of SageMath, which is a free and open source software system that used Python as the interface language. It is suitable. It is a general purpose language and suitable for scientific computing with the modules, with the packages NumPy, SciPy, SymPy. So we will, in this lecture, use numerical integration as our running example. So I will introduce this via scripts that are running at the terminal prompt. You can see from the layout in this pre-recording that I have a Jupyter notebook waiting. The Jupyter stands for Julia, Python, R, and many others. So it is a good exercise to make everything run also from within a Python notebook. I will do this with Julia, but not so much with Python. So my goal is to explain how to develop a parallel prototype of an implementation. Of course, I must say that Python is not an efficient language, and people who are interested in performance may immediately stop me here and say that, well, hey, you should not use Python. To that, I would say that NumPy and SciPy uses vectorization. So when you are using NumPy, SciPy, and the packages, you actually are executing compiled code. Here is our computation. Interactivity is important. So this is done at the command shell. These commands are typed in, and you get an immediate reply. So in a way, if you have never used Python, then the familiarity aspect is not here, but I think the brevity, the shortness of the approach is important, and the the interaction and the immediacy of the type of computation. I should say that the computation that we are doing here is not really useful approximation. If you are interested in approximating pi, then this is a bad way of doing it. But that's actually also intentionally. I want a computation that takes a couple of seconds. So I'm combining SciPy, the Simpson rule. I'm combining the vectorization that is available in NumPy. So what is so good with using NumPy is that there are no explicit Python loops. So you see the statements R equals we define a grid where we are going to evaluate our function, and the function is evaluated in the statement y equals f of r. So that's one vectorized instruction that is executed by compiled code. You see, I'm importing also the square root function from the scientific mathematical library. So that is a square root function that can take vectors on input. So the R is essentially a whole array of numbers. And instead of having an explicit loop, an explicit Python loop running over this, I'm already being much more efficient by running the compiled codes. So I'm not starting from a naive implementation here. Okay, so then the scripts are still very short. So here is a computation that scales things up. So I want something that takes seconds. So in a loop, I will run the instructions. So for k going from 2 till 8, the number of function evaluations will increase. So at 10 to the power 6, I'm at 1 million, then I go to 10 million, then I go to 100 million. So I still want to have a meaningful computation. You can see that at 100 million function evaluations, I get actually pi close to machine precision. So the error is 10 to the power minus 13. So this is a converging process. It is also immediate, so you do not really need a parallel computer to do this. So we are going for speedup. So I'm running this on, I have prepared the runs on a Windows laptop. For that I run this on a PowerShell and I do the measure command. On a Linux and a Mac terminal you do time. That will give you the wall clock time. Here is what you get on Windows. It's not the best format, I think, but on the other hand, you can see immediately off that it finishes in 5 seconds and almost 6 seconds, so 5 seconds and 785 milliseconds. So this was executed on an 8-core Intel laptop, which supports hyperthreading. So logically, if you want to get most of it, you can actually work with 16-threaded computation. For this computation, it's actually important the amount of internal memory as well. I will get back to that. Okay, so it's a personal laptop. So with so I had 5 seconds, 700 milliseconds, and actually most of the time actually went to the 100 million run. So in every run we got, so I should also have pointed out that, perhaps I can scroll back, so you can see how bad this is. You do 10 times more work for one decimal place. So it's actually not a good algorithm. But we sidetracked this. So Simpson's rule is also some rule which approximates the function. So we have the area under the unit circle. We approximate this with parabolas. So in some sense the algorithm is not efficient, but it's not entirely naive either. So I kind of black box this. So numerical analysis, we can spend some time in deriving the Simpson rule, but that's taken here for granted as available in the software. Okay, so now here is the key question, 15 minutes into this lecture. So we have a very simple program. So you can see the number of lines, not more than 7 lines of code if I subtract the print statement. So a very short script that does a very complicated computation essentially, and it takes 5 seconds. So given that we are impatient, can we improve on the 5 seconds given that we are running this on a multi-core computer. So notice that I had my original script Simpson for pi. Here I have the Simpson for pi 1. So this is the the sequential implementation. So if you are starting to compare things, it's good to have somehow a reference. So this is the simple code how we would run it. So we are going to use that as our reference. Okay, familiarity. So we are familiar with Python. We have a code that we know is correct. So we want to stay within Python, and we want to use something that is built in Python. So in Python we have the multiprocessing module. So Python is a language that comes with batteries included. So we import the multiprocessing module. What does this multiprocessing module do for us? It launches processes, which is essentially a process is synonymous here for program. It launches another Python interpreter and executes the program that we want. It also takes care of the interprocess communication. So again, if you are not familiar with, if you have a basic familiarity with Python, it does not take much to learn the multiprocessing module. It is built in, no installation required. I should say here that parallelism is not equal to concurrency. Concurrent execution means that the same thing happens logically at the same time but not simultaneously. Think of the polite dinner conversation. You eat but you don't talk. You talk but you don't eat. So nevertheless, during the dinner, both activities happen concurrently. So with Python also has a multi-threading module, which is useful to introduce concurrent programming, and it has its uses, but it's not useful for parallelism. You will not get speed up of this. That is an aside. So here is now the introduction to the multiprocessing module. So in some sense, this is a side step to make this lecture self-contained. So I'm going to simulate the multiprocessed execution. So what actually is happening, a new process is forked, is the terminology. or spawned, and what every process does, it says hello. It has a unique identification number, a process identification number that it gets from the operating system, and then it will sleep for a while. And then it will terminate itself after have one final message printed. So we have the process that is imported from the multiprocessing. So here is how we make our processes. We start the processes, and actually there are here two processes, but there is also a third process. So that's the main process. So the processes are started, and then the main process has to wait. So this is where the join comes in here. If you would not have the join, then the main process would just terminate. Now the main process has to sleep as well, wait for the two processes to finish. So the argument to the process method is the function say hello, and then the arguments are the names and the arguments. So perhaps I should have indicated this. So there are two arguments. So there is the name. So I named them A and B in the main process. And then there is the amount that they sleep. So I will launch A sooner, but it has to sleep longer. So B will terminate sooner. So this is a very nice way to experiment with multiprocessing. And you will have true parallelism, as we will experience. So here is the execution. You can launch this on the PowerShell or at a prompt, and you see the processes. You see that B sleeps 1 second and wakes up sooner before A. So it's a very predictable. You can see the process IDs. So we have a sequence of numbers. The main process has an ID, and then you have the other process IDs. So via the operating system, you can actually verify this and query. Although perhaps for the sake of experiment, you may increase the number of seconds, but just to make sure that things are visible. But you can verify this. So these numbers are there. So Python works. That's the essence. There's something else that we would need. That I will explain how the inter-process communication works. But we are interested in numerical integration. So numerical integration is a method that lends itself very well to parallelism via the linearity of the integral operator. So you can subdivide the integration interval AB. Here we don't know anything better but to have it in equal parts. So we have P processes. We subdivide the interval in P equal parts. So you see already the benefit of this high level tools. I can experiment with concepts of making things run in parallel. So the very important operation of numerical integration lends itself naturally quite well to parallelism via the linearity of the integral operator. So the integral of a sum is the sum of the integrals. You could also that's another functional decomposition, I should say. So there are a lot of avenues here to explore. But this is the main idea on how we will make this run in parallel. So here you see the revised script. So this is now the Simpson for Pi 2. So that's what I will use. And I'm importing not only process, but I'm also importing Q. So q is the q, the little q here as the last argument is actually the q where I put the results. So every process has a queue and it puts its result there. So every process computes its part of the pie. So between integrating between A and B. So the A and the B are also local parameters. So there is the global A and B of the whole integration interval. But then there is also the A and B that will be passed on to the processes. So we pass the number, the beginning of each interval, the end of each interval, also the function, and then the number of intervals we do, the sub-intervals of A, B. So recursion, if you like, but you see that the essence of what we practice interactively is here simply there. So we have the vectorization that is applied. It works, so we have practiced this interactively. So the correctness, in some sense, if we have the correct partitioning of our interval, the correctness is hereby also verified. Okay, I have to do some technicality here. I want to do the timing without having to enter any input and without having to hard code the number of processes either, because I want to do this with 4 processes, with 8 processes, starting with 2 processes. So that is where I'm using this command line argument here. So this is the command line argument, which is working platform independent. If you do this on a Windows PowerShell or on a Linux on a Mac, a terminal window, this works. So you can run this script then without any input. The script is user-friendly. If the user forgets this argument, then the user will be prompted. Actually, will be told to enter it at the command line. Okay, so now comes the use of the queue. So I have my function that is called CRC for the circle. So I have this segment of the circle between 0 and 1. So that's this quarter of the pie. I compute, so I'm still going to do this for 100 million function evaluations. So every processor, so the number of processors is this NPR, not a radio station. So the NPR was passed through the command line. Know that Python 3, I have to use the proper integer division. I'm then using the floating point division with the interval. So it's the interval 0 to 1. So every interval here gets adjusted. So the left and the right, it starts with 0 and the length of the every subinterval. And you see here with the tuple assignments, it gets adjusted. Now come the specific multiprocessing commands. I will create for every process a queue. So I will pass the queues. So what gets passed is when we create a process. Actually, I'm creating here a list of processes. So it's initialized here to the empty list. I'm creating a list of processes, passing the name of the function, the left and the right bound of the integral, the number of samples, the number of function evaluations that every process will do, and then I pass the queue. So that's the main technicality here. And then we have when I was demonstrating the multiprocessing module, we had the start and the join. So now we have separated the declaration of the processes, the making of the list of objects, from the actual execution. So we have the forking and then we have the joining of the processes that is done here in one loop. Then there is the put to queue, then there is the get. So every process does a put before termination, and the main process will do a get. So in this loop here. So this is written within the proper list comprehension high-level syntax from Python. If you have never seen Python, then, well, this is an advertisement. If you're familiar with Python, then you're doing parallel processing already within your familiar environment. So we are doing high-level parallel programming. And this is something that is and should be taught within also a regular Python class. But here within this course, we can use this high-level formalism to introduce many concepts of parallelism. Okay, does it now work? Because that's the prototyping. That's also the argument for Python, that it's a high productivity environment, so you get things done. And indeed, with some little modification, we actually have speedups. The speedups are far not impressive, but if you're interested in wall clock time, you go from 5.2 seconds to 3.9 seconds. You see, with two processors, you get a 30% speedup. That's also what you could say. You don't even have two. You also see the scalability. So there's kind of a sweet spot here. Perhaps I should have tried 3 and 5. But you see that if I start doubling again, I have an 8-core machine. And if I go to 8, it actually doesn't improve anymore. Okay, so that's still a motivation to go to another environment. So let's go to a faster machine. So here is so I said that this is personal. Well, this is still a personal supercomputer. So this is the fast workstation, 22 cores. And here is where the reasoning goes. Why is that not so efficient on my laptop? Well, because of the memory consumption. Here on this computer, I have 256 gigabyte of internal memory. And I should say that as far as numerical integration go, we actually store all function evaluations and then we sum them up. So in some sense, this is extremely wasteful in terms of memory consumption. So essentially only need the current number of function evaluations that you are running. So from a performance perspective, this was a horrible idea to work, but it is a very nice, clean way to write things up. It also is an illustration that modern workstations come with abundance of memory. So memory starts to be critical as well. Python is also a language where memory is managed for you. So that is another benefit, but also sometimes not. Okay, I'm more than halfway in what I have budgeted for this lecture. Let me now go to Julia. So Julia offers a new approach to numerical computing. So there are many new languages invented all the time. Julia is a language that's now more than 10 years old, but still very modern. that's specifically targeted to scientific computing. So that also what makes it very exciting. It's also sufficient general purpose, so to cover. It's also coming just like Python with a huge ecosystem. Chances if you have to do anything that is classical scientific computing, chances are really great that somebody has already written a package for it. Or has written a wrapper, Julia wrapper. So if the original application was written in another language, so that you can use it from within Julia. So that is one of the points that is not mentioned here in this diagram. There are some issues here. I like this diagram when coded well. So this is very important here. One often makes the comparison between compiled, so Julia is a compiled language. One can make also Python compiled because there is Cython. And we have already applied vectorization in our order. So Python can just be competitive. So the green is also shared with Python. So the green and the purple is actually shared with both Python. So Julia has an advantage over Python because of its code generation. Okay, what are we going to do? I may show the Jupyter notebook, or I actually really should show it, but let me first go through the slides. The Jupyter notebook is another common standard now for interactive computations, which allows to document and describe the documentations. I'm actually still using slides, but I could actually teach this course entirely from within a Jupyter notebook, as it allows markdown styles to describe the computations. In a Julia environment, you can install a Julia kernel, and here on this laptop I have 16 logical threads. I can install a kernel so that everything can run to 16 threads. Now, I should have said right from the beginning there is one way to do high-level parallelism, and that is by running software that has the parallel option in it. So we will do matrix multiplication, and that has already been provided by the basic linear algebra subroutines. It's still interesting to do. I mentioned scalability in the last lecture, and scalability runs through this course. So in order for a parallel computation to be meaningful, the problem size must be large enough. I also hinted at this with the 100 million function evaluations with Python. So just as with the previous computation, there's actually not much that you need to add. So Julia is targeted to scientific computation. The linear algebra is a module that is built in. So you do not need to install extra packages even. And here you see one can time the matrix multiplication. I prepared this for 8,000. So again, if you are taking a linear algebra by hand course, you may have worked with 4-dimensional matrices. So don't do this with 4-dimensional matrices. We work immediately with 8,000. The 32 gigabyte internal memory worked fine here. We have 10 seconds, and I'm actually here immediately giving the parallelism. So if you double the threads from 2 to 4, you go from 10 seconds to 6 seconds, which is actually quite nice. Again, this is all executed in optimized compiled code. All right. I should say that matrix multiplication might not be so attractive, but many scientific applications translate into matrix multiplication. So if you can do that fast, then you can solve many problems, many scientific problems. Okay, numerical integration again. So there is the Simpson rule that we have applied. So as an exercise, I will ask you to do the Simpson rule in Julia. And as an exercise in Python, you do the Monte Carlo simulation. So here you see the approximation of pi again. So in the first part, I computed, we did 100 million function evaluations with the Simpson rule for that approximation here. If that was not inefficient enough, we can do something even more inefficient. We can take samples and just do a Monte Carlo simulation, count how many of our random samples landed within that slice of the pie. So that is the algorithm. To be not completely causing the overhead, I picked a dedicated random number generator. So functions in Julia are very easy to define. So here is a random number generator defined and a one-liner. Julia will compile this efficiently because I'm actually here indicating the typing. So I did not indicate this with Python, but most recent improvements of Python also actually allow, and Cython does this too, that you give the typing information. So that's also a way to make your code run more efficiently. Julia, for if you're not familiar with it, the documentation string comes before the actual function implementation. So this is kind of nice. Documentation is important. We will go more into detail. So Monte Carlo is a very important application. I mentioned it also in the last lecture. It's critical here that if you run this with many processors, that they don't start to generate the same sequence of random numbers. That's why I was careful here that every thread has a unique identification number, and that is used to seed as the starting number in the random number generator. So in a way, the algorithm is very simple. I generate a random number for x, a random number for y, and then we just count up the number of successes. So in the past, when we taught programming, there was pseudocode, but now the syntax has been so concise and clear that actually the need for pseudocode has actually a little bit diminished. And personally, I find often that working code is often the best definition for an algorithm because it is unambiguous once it gets executed, once it gets verified through its execution. All right, now here is the selling point. I'm running out of time. I have budgeted 50 minutes for this lecture, but you can see that I will get there. I will get within time with the slides because here is how short things are. I have essentially only one parallel for loop. So the for loop is with this acroll. It's kind of with a directive. So it will be executed with the 16 threads, and every thread will actually run one step in this loop. So this loop goes from 1 to the number of threads, and then every thread writes in this array estimates. And somehow I will have to make this clear now in the Jupyter notebook. I may not have copied everything over. So there is this array estimates. If you do multi-threading, so this is now true multi-threading, not the multiprocessing. So now the multi-threading, that there is shared memory. One has to make sure that every thread writes into a separate memory location. And that is taken care of here. So every thread has a unique identification number and writes in a unique spot. That is then collected. So the mean is used here to compute the average. I will show the flash up essentially the Jupyter notebook, but here you see again on the same fast workstation. I was doing this already quite early, so this is an old version of Julia. So Julia came right from the beginning, from the early on start already with multi-threading enabled, which was very good. And you see that I get actually doing very well. So I go from, without almost normal, with very simple high level code, I go from 1 minute to 10 seconds with 7 processes. So this is a very nice result essentially. Okay, let me try to flip context here. I go to flash up the high level multi-threading. So this is my Jupyter notebook with a kernel. So let me see if I can show this. So I have another kernel that I'm demonstrating here. On this laptop I have already multiple installations of Julia. I have experienced that with the Jupyter notebook it may be sensitive to the kernel. So the information about the kernel can be manually edited in the file. For this run I'm still working with not the most recent current version, but I'm working with 1.8. So this Jupyter notebook runs with the 1.8. So the slides had the declaration of the kernel. So this is the kernel that is running now. So let me go back to the Jupyter notebook. You see, as a confirmation, if I'm so you have my section heading, multi-threading. If I'm using this base threads module and I have my input, I'm using this threads module, then just as I would type into a notebook and into an interactive kernel, you can see that I have 16 threads available, and this actually is a confirmation. For just if you are following along, here are the statements. So 2 statements. If everything is installed correctly in your environment, then updating this is just very straightforward. The parallel matrix multiplication that I illustrated here is executed. So I'm scrolling through this. The semicolon I didn't talk about. So you actually do not want to see all 8,000 by 8,000 numbers scrolling through your screen. So the semicolon in Julia means suppress the output. We set the number of threads, and then the computation gets executed. Here we actually see the output. Not that useful, except perhaps if the numbers look kind of, I don't know what to say much of it. So the compilation time is also there. 5% was compilation time. So if you redo it, that 5% falls off. And doubling the number of threads, then you see the speed up. So here it is. So we went from 10 seconds to 6 seconds. Okay, something that I didn't show. So there is the peak performance. So um, it's another feature of the linear algebra module. So for the Gaussian elimination, you can actually see how many floating point operations that this code can do. So this is the 10 to the power 11 floating point operations. So 10 to the power 6 is a million if you would think about megaflops, but we think about billions when we think about 10 to the power 9. And here you see that we get to 10 to the power 11. So we actually do have a very high gigaflops, very high number of gigaflops that can be realized with this implementation. Again, this illustrates the notion of scalability. On this laptop, 8000 was kind of the sweet spot. So with 8000, you get the best number. 4000, it starts to level off, and well, with 8000, 16,000, you still have a high number. Okay, so 200 gigaflops if the 16 threads are used on this computer. Not bad. So this illustrates somehow that Julia allows to really get the most out of your computer. So it's geared towards high performance. Okay, I'm actually running out of time. What I will still have to show now is how the estimates came in. And I forgot to copy this on the slides, but here you see the statement. So the statement is the estimates. So with the estimates, you can see, something went wrong when I was trying to rescale things. Let me hope that it works out. So something that was missing on the slides, every thread has to write to a separate location. So here I have to make sure that the estimates that there is space for 16 zeros. So that is what the zeros is doing. It's allocating, it's making a vector for to make sure that there is sufficient space. Okay, that's the end of the lecture essentially. So I can scroll through the, so you can see that I will post this notebook as well, that this will run. So you get to experience the speed up, you get to see that everything works, and almost all computers, and actually you will not find a one-core laptop, so this should definitely work on your laptop as well, even if you not have a high end. Let me take one final comment here. So the lecture actually is not to the final end. So supercomputing, or at least parallel programming, is for everybody. So you can experience most of the important concepts on supercomputing, practice with them already on your laptop in a familiar environment. Let this be Python or Julia. Both are actually suitable. And there are two suggested exercises. So here is how one could code up the Monte Carlo with high-level Python. That's make it run in parallel is actually the exercise here, starting from this piece of code. Then you can also, the Simpson rule is definitely also implemented in Julia. Develop a parallel version for that way to approximate pi. Okay, I'm running 5 minutes over time, but I hope that this lecture was worthwhile the trouble. In this course in supercomputing, we will illustrate the concepts. I will go to lower level languages because they allow me to illustrate also the memory movements. But nevertheless, everything can be done and executed from within a high level parallel language. So there is MPI for Pi, message passing with Python, and there is also message passing with Julia. And that is what we will begin with in the second week in this course. So thank you for watching.